All right, so here we go with naming transition metals. So you should have open your transition metal naming handout, and here we go. So the first question is a bit of a warm-up just to get you thinking about why we actually have this additional system for naming transition metals. So think about what you've done so far. So you figured out the ionic naming, there's the crisscrossing, there is changing the ending to "ide," all of that stuff. Then we added polyatomic ions, and that was kind of another level, using parentheses, some different names. And then the third level here is transition metals, and this is the last level, I promise. And in order to kind of illustrate why we need a system for transition metals, you have this warm-up question right here. So it says, can you determine the charges of the cations and anions in these two compounds without looking on your periodic table? So that's the kickers. Can you do this without looking at your table? Looking at this first one, Fe2O3. In your head, in order to figure that out, you kind of have to do a reverse crisscross. You know how you bring numbers that are up here, you bring them down? Well, in this case, imagine doing the opposite. What if you could rewind that and break Fe2O3 back up into the ions that it started with? Well, if you could do that, you'd have Fe3+, remember it's the cation because it comes first, and then O2-. Let's do the same thing down here for FeCl2. If you could also rewind the tape, essentially, what would the charges become or be at the beginning before you actually did the crisscross and came down to your final formula? We have Fe2+, Cl-. Okay, so take a look at the irons here, and this is what makes things transition metals special. So iron is a transition metal, and if you'll notice, it has a 3+, and then it also has a 2+. And this is what makes transition metals extra special, I guess, is that transition metals can have more than one charge. And for the record, we're always going to be talking about cations. Metals are always going to give away their electrons, so you're always going to be talking about positively charged ions. But the kicker is that they can have more than one. That's kind of why we've been skipping them up until this point. If you think about alkaline metals or alkaline earths or halogens or things like that, they have these beautiful clear patterns. Halogens will always be a -1. Alkalis will always be a +1. Transition metals, you cannot make those statements. And so what we need is we kind of need a separate naming system because of this fact, the fact that they can have more than one charge. There are, however, of course, two exceptions to this statement that they can have more than one charge. And you kind of got to tuck these away in your memory, but they're pretty straightforward. The first transition metal that cannot have more than one charge is zinc, and zinc will always be 2+, always, always. The second one is silver. Silver will always be 1+. So those are two that this whole system that I'm about to show you does not apply. So you can tuck those away, silver and zinc. So let's go down to how we actually use this. I'm going to teach you a system called the stock system. And for years, I just assumed it was called the stock system because, like, that's the standard stock way of doing it. But it turns out it's actually, I learned recently, it's actually named after a guy. It's named after a Swedish chemist, last name of Stock. And so what he did was he looked at this problem. He looked at the fact, oh gosh, iron can be 3+, sometimes it can be 2+. How can we tell the difference if we just call it iron? The answer to that problem is we add something in there. The stock system uses Roman numerals. And the examples that you're going to see, I don't think we're ever going to go higher than 5. So just to review, Roman numeral 1 is like a capital I, 2, and I realize that you're probably typing this, so if that's the case, then it's just like an I next to each other, capital I, capital I. 3 is 3, and then 4 is I and then V, and then 5 is just a capital V. So those are the Roman numerals, just to review those. So let's look at how that comes into play. So I'm going to look at, if I give you a formula, how to name it. So again, the problem with this one is that if we just call this iron chloride, there's a bit of a problem because iron can be a 2 plus, like we've seen up here. It could also be a 3 plus. How do we tell the difference? Here's what we do. I give you a couple of different steps. The first one is you name the cation and anion. Well, I kind of already did that for you right up here, iron chloride. So we'll write it down here just to follow the rules. Iron chloride. Step 2. If the metal involved, the thing that's listed first, is a transition metal, you have to use a Roman numeral. So in this case, yes, iron is a transition metal, so a Roman numeral is needed. Step 3, it says figure out what the Roman numeral should be. If I could pick one thing in here that people make the biggest mistake on, and most consistently, it's step 3 right here. The Roman numeral represents the cation charge. The most common mistake that I see is people forgetting that or messing that up. So, for example, in this case, we figured out, like I had you do up here, when it's FeCl2, you kind of rewind the tape in your head. Fe has a 2 plus charge, and so the Roman numeral in this case will be a 2. In Roman numeral speak, I translate that to I. So my final answer is iron 2 chloride. And in terms of checking your work, what I want you to do is make sure that you've double-checked that you're looking at the charge of the cation. Like I said, the thing that I see people mess up the most is they think it has to do with how many irons there are. It is not iron 1 chloride because there's 1 iron. That is wrong. So I'm going to write it and then I'm going to switch colors and X it out very dramatically. It is not iron 1 chloride. It represents the charge of the cation, 2 plus. It does not tell us how many there are. You have to figure that out on your own as you go. Okay, so that's what to do if we're given a formula and we have to go to a name. Let's look at what happens if we have to go the other way around. So if I'm given a name and I have to go to a formula. So in this case, I gave you iron 3 oxide. So step 1, translate the name into the ions. So what I do is I take iron, and that's just writing down the symbols, Fe, and then oxide is going to be O. And let's look at what I know here. The 3, remember, the 3 does not tell me that there are 3 irons. No, the 3 tells me that is the charge of the iron. So that means iron is going to be 3 plus. I know that because there's the Roman numeral right there. Oxide, that's oxygen. I'd have to get that from looking on the periodic table. So that, hopefully you are very comfortable with doing this by now, that would be a -2. So we put the ions next to each other in step 2. Fe3 plus, O2 minus, and then we crisscross. Remember, that's when we drop things down. The plus and the minus do not come along for the ride. In fact, they disappear, but the numbers are what move. So we're left with Fe2O3. So this is the formula for iron 3 oxide. Again, I want to emphasize the 3 tells us the charge of the iron. It does not tell us how many irons there are. Okay, there are 4 that I want to do with you just to make sure that you're feeling good about this. So the first one is a name or a formula to name problem. I've given you the compound, you have to name it for me. So just to review our steps, this is kind of one of those first examples that we looked at. First thing is we're going to name the pieces and then figure out what the Roman numeral should be. Okay, so Ni, if you look on your periodic table, is nickel. I'm going to leave a little space because there probably will have to be something that goes in between, like a Roman numeral. And then I is iodide. Now the question is, okay, nickel's a Roman numeral. I'm going to need some nickel is a transition metal. I'm going to need a Roman numeral. What Roman numeral am I going to need? In order to figure that out, you have to mentally rewind the tape, just like we did over here. You're going to have to back it up in your head and figure out, okay, kind of do a reverse crisscross. So the 2 that's down here is actually going to come up to be with the nickel. And then remember, there's an invisible 1 right there, and that's going to come and be with the iodine. So the number that goes in between the parentheses is the charge of the metal, not the quantity, but the charge. So this is nickel 2 iodide. Let's pop down to letter B here. Iron 2 oxide. Fe is the symbol. O is the symbol. So if you'll notice, this looks really similar to this one. Up here, it was iron 3 oxide. Let's look at what happens when it's iron 2. So the 2 here tells us that this is going to be a 2 plus. The O tells us it's going to be a 2 minus. We crisscross. We're left with Fe2O2. But remember, why is that wrong? Why would I not stop there? Because I can reduce this further. They can both be reduced by the common factor to down to FeO. All right, Cu2S. Here we go. Cu is copper. S is sulfur. In order to change that ending to what I needed, I'm going to change it to sulfide. I'm leaving a space in the middle, though, because I know something's going to have to go in those parentheses there. So let's see if we can figure out what that is. Looking at Cu2S, let's rewind the tape. The 2 moves. And remember, there's an invisible 1 here, and that's going to move. We're going to be left with Cu1 plus and S2 minus. The number that goes in the parentheses is the charge on the copper. So it's copper 1 sulfide. Last one. Here we go. Cobalt 2 selenide. Or selenide, depends on how you want to say it. So it's CO is my cobalt. Selenium is Se. From looking on the table, hopefully you feel comfortable about recognizing that selenium is going to be a -2. Cobalt, I don't know what that charge is going to be, so I look here. The Roman numeral tells me it's going to be a 2 plus. So I have things to crisscross now. CO2, Se2. But just like this one over here, I'm not done yet. If I just left it like that, that would be wrong. The final step is reducing it all the way down to COSE. All right, and that is what you need to know about transition metal naming.